It's something we'll run into a lot with asymptotic expansions, is that sometimes there's not a feasible Taylor series expansion around some epsilon goes to zero limit. So for instance, there's no algebraic expansion that works for e to the minus 1 over epsilon, for instance, because that is exponentially small compared to any algebraic term that you could have in a power series. And so when you can't do an expansion like that, you're not really going to have any luck with a Taylor series. And that can happen a lot in transcendental equations. But if you start iterating your map, you may find that eventually you'll start to create functions where you can perform those expansions. And so, so we went through an example or two of that. We had concluded on this transcendental example. Okay, and let me just finish that off now. So let's say that we're trying to solve the equation x plus 1 plus epsilon hyperbolic secant x over epsilon. And in this case, we have the line, let's say -1 minus x here. If I plot epsilon hyperbolic secant x over epsilon, this intersection point here is going to be somewhere near -1. Okay, here's x. Okay, and we said that we would use an iterative procedure to try and find this root. Okay, we know that it starts out close to -1. Okay, so our x0 in this case would be -1. Okay, now if we plug this in, there's a couple things that we want to consider when we're making the truncation to move on to the next step. Okay, first of all, okay, notice that if I write out hyperbolic secant like this, okay, I see that in the denominator, I have e to the 1 over epsilon, which is quite large, okay, as epsilon gets small, and e to the minus 1 over epsilon, which is exponentially small as epsilon gets small, okay? So that means that this term here is negligible, okay? Not even in an algebraic sense, but in an exponentially small sense, okay? So e to the minus 1 over epsilon is much smaller than e to the 1 over epsilon. So that means that I can essentially drop this term. So I have 1 minus 2 epsilon e to the minus 1 over epsilon. And remember, I can't really Taylor expand this, okay, to get some sort of an algebraic power series expansion. So it's unlikely that I might have arrived at this just by sort of guessing an expansion. So that's where the iterative method comes in handy, okay? So the next step in the method then is to take this refined expansion that I have now, right, and plug it in again into my map, okay? So I lost a little index there. Okay, so I have exp of 1 over epsilon plus 2 e to the minus 1 over epsilon plus exponential of 1 over epsilon minus 2 e to the minus 1 over epsilon. All this to the -1, okay? And again, 1 over epsilon is going to be much larger than e to the minus 1 over epsilon. So I can drop out the e to the minus 1 over epsilon terms there. And I'm just left with, let me write this as just, so asymptotically, this goes to minus 1 minus 2 epsilon exponential of 1 over epsilon plus exponential of minus 1 over epsilon to the minus 1, okay? And I can then subsequently expand this out into minus 1 and keeping the term that I had last time. So 2 epsilon e to the minus 1 over epsilon, right? And then essentially Taylor expanding about e to the minus 1 over epsilon for this function here, right? Which is just going to be 1 over this plus this, okay? I can add on a correction term now with the Taylor expansion of the 1 over a plus b function here. And that next term in the expansion is going to give me 2 epsilon e to the minus 1 over epsilon, and then e to the 2 over epsilon, okay? So the next term down in order is going to be exponentially small, but it's going to be minus e to the minus 3 over epsilon instead of just 1 over epsilon. So if I write now what my new approximation is going to be, okay, I now have this additional e to the minus 3 over epsilon term. And so remember, when you're performing the iterative method, think about each time you pass your old guess through the map, right? And you expand and you retain terms, you want to effectively keep the same original terms that you had before and add on a term of higher order. And hopefully you can do that by Taylor expansions, but sometimes you have to do some factoring and manipulation in order to be able to identify that.
Will you ever have the case where some of the older terms do get updated for like a couple iterations, but then steady out?
You're saying, can that happen?
Mm-hmm.
Yeah, so that can happen if you don't, if you, well, it can certainly happen if you don't keep enough terms the first time. And yeah, I mean, it's possible that you could have, you know, you could plug your previous guess in, and somehow you would end up adding on terms of similar order in that case. And you know, that could be for a number of reasons, right? That, remember, you always have a choice, right, of what you choose for your map. And so typically you'd like to choose a map that sort of separates things out like this into order 1 terms, and then an update which is going to be of smaller order than your leading order term. If you don't have a map that does that, then yeah, it's possible what you're saying.
Okay.
Happen. So when you're seeking to construct a map from your original equation, you should endeavor to construct a map like this, which has sort of separate sort of first and higher order terms.
Can you say again what we Taylor expanded about in this sesh line? at the bottom of this page? Because that is just sesh written out again, right? But now we're doing something different than we did the first time.
Well, yeah, because you have a new you have a new set of terms now, right? I see what you're saying is that, yes, essentially we have the same thing that we had before, right?
Right.
So why didn't we do this in the first place? It's
I'm also asking,
basically
what
'cause
did we do
each
again?
time we want to sort of incrementally add another term on, right? But you can see here, right, we probably could have gotten both of these terms this time.
Well,
But we,
can you say again what we did, Taylor, expand about?
yeah, so just it's, you know, the function 1 over e to the 1 over epsilon plus e to the minus 1 over epsilon. So the leading order term is just 1 over e to the 1 over epsilon, right?
Mhm.
And then the correction to that is adding on this term, right? So your f of 0, if you like, is just 1 over e to the 1 over epsilon, which gives you this term, right? And then this is your perturbation. So that's what you Taylor expand about this, and you add on this as a correction.
Okay.
Okay. All right. Oh, there we go. Okay. So, okay, so that's a couple examples of transcendental equations. You'll have a chance to practice that on your homework. Any other questions before we move on? Yeah, I mean, I know that, you know, the devil's in the details with these things, and yeah, I would say the best guidance for iterative method is to just try and construct a nicely separated iterative map so that you have a higher and lower order term involved. You certainly want to try and avoid a map that's going to cause your approximation to sort of blow up over time. Expand where possible, but do it systematically so that each time you apply the map, you only add another one more term in the expansion, and you try and maintain all the other terms that you had before. Okay, so the last thing we'll go over, and this is sort of the last section of this chapter in Hinch, is eigenvalue problems. Okay, how do you handle this perturbatively? And so we'll start by considering sort of a classic perturbation problem for eigenvalues, where we have some matrix A, but this could be also a linear operator, right? Could be a differential operator, it could be an integral operator. And then we have some perturbation to that. And even though it's a leading order, we have this eigenvalue problem. We're going to allow the perturbation to be potentially nonlinear. Okay, so this is a common problem in you know, approximate solutions of PDE, differential equations. It comes up a lot when you're looking at sort of mathematical model building from physical systems. Okay, sort of linearizing based on some small perturbation to a linear system. Okay, and at order epsilon to the 0, I'm going to just write out the eigenvalue problem. I'm going to call little a our eigenvalue. Okay, so we'll assume here that a is a single simple root, okay? This is going to be an eigenvalue of our leading order equation. And in this case, if we transpose our problem, we can write it as E dagger A, and then A, E dagger. And we'll say that E dagger, right, is going to be orthogonal to eigenvectors of other eigenvalues, okay? This is like our left eigenvector of A associated with little a, okay? So we're specifying a particular eigenvalue, and now we're going to move forward with what happens when we perturb about this, okay? So what's the process here? We're going to assume some expansion. We'll assume it's regular, okay? What do I mean by that? I just have a nice power series expansion of my original eigenvalue and eigenvector, okay? So lambda epsilon is going to be A plus epsilon lambda 1 plus epsilon squared lambda 2, so on and so on, okay? And if we substitute, okay, substitute in, okay, and we expand, then at epsilon to the 0, again, we just get A, E equals A, E, okay? At epsilon to the 1, we get A x1 plus, now, B E is equal to A x1 plus lambda 1 E, okay? So I can rewrite this as follows: A minus little a times x1 is equal to lambda 1 E minus B E, okay? What do we already know here? We know big A, we know little a, okay? We know E. We don't know lambda 1, okay? Well, we also know B of E, and we don't know x1, okay? So those are our unknowns. So how do we specify these two things? This is sort of like a new eigenvalue problem, but we have these sort of inhomogeneities essentially in it, okay? So now, in order to specify these things, we're going to take an inner product with our left eigenvector, E dagger. And what do we get? We get E dagger A minus A x1 is equal to E dagger A x1 minus A E dagger x1 is equal to A E dagger x1 minus A E dagger x1, okay, which all of this is going to cancel out and give us 0, okay? So if I just take E dagger's inner product with left-hand side, I get that the left-hand side should just be 0, okay? What about the right-hand side? So the left-hand side is 0. The just a scalar 0. If I take the inner product with the right-hand side, I get that E dagger lambda 1 E minus B E. This should equal 0, okay? Well, if you look at that equation that I have now, okay, it does not involve x1, right? And it just involves lambda 1. So I can rearrange things, and I end up with lambda 1 is equal to E dagger, okay? B E divided by E dagger, we could say dotted with E. So just to be clear, let's think about these as dot products, right? So we know we have a scalar on top and a scalar on the bottom, okay? So I've specified what my correction to the eigenvalue is. It's the left eigenvector of my original eigenvalue, my simple eigenvalue, dotted with my perturbation, divided by E dagger dotted with E, okay? And if I have self-adjointness or something like that, then this would just be E itself, so that you could think of this as like the norm of E squared, okay? So you could sort of think of this as the projection of your perturbation along the eigendimension of my original eigenvalue, normalized by the eigenvector itself, okay? So that's what this perturbation does to that particular eigenvalue. Okay, it just gives you an additional contribution along the projected dimension of the eigenvector itself. If it's purely self-adjoint, for instance, if you have a self-adjoint operator. Okay, so this also allows me now to compute the eigenvector correction. So I have A minus little a, x1. This is equal to minus BE plus E dotted with BE divided by E dagger dotted with E times E, okay? Or I can write this in shorthand, okay? And you can call this BE. And I'm going to write that little perp symbol there. And I'll say, in other words, this is the part of minus BE perpendicular to E, okay? So the updated eigenvector now is going to involve whatever part of minus BE, okay, is perpendicular to E in this case, okay? Because I'm basically adding on the part that is in line or projected along E in this case. All right, so that's how the eigenvector gets updated. So x1 equals minus a inverse, okay, and I'll define that shortly. B E perp there plus K1 E. All right, so where this here is going to be like a restricted inverse in the space orthogonal to E, which means that you also have to add on, some correction based on the fact that you also could have some contributions in the direction of E for this particular eigenvector. And that shouldn't be surprising, right? Because the original eigenvector was E, right? So you should just be able to add on any scaling of E and still have a legal eigenvector in this case, okay? We could also use eigenvectors, okay? Ej, and we would get x1 is equal to the sum over j over all of our eigenvectors, okay? These left eigenvectors, so this will be Ej dagger dotted with B E, A minus A J, that'll be all the other eigenvalues, Ej dagger dotted with Ej, Ej plus K1, okay? So if I wrote it out in terms of eigenvectors, right, I would just have all of these projections along the all of the other eigendimensions scaled by the difference in the eigenvalues associated with each of those, which is why this formula is only going to work for simple eigenvalues in this case. All right. So, even if the sort of details of what all this means are a bit murky, hopefully the procedure is clear, okay? You're going to expand as you do before, and you're just going to use linear algebra in order to solve the resulting equations that you have. And the tool that you leverage in order to isolate the eigenvalue, in this case, is the orthogonality of the left eigenvector to all the other eigenvalues, all the other eigenvectors, okay? All right, so questions about this?
So did we mention this is only for symmetric or Hermitian matrices so that we have that orthogonality or an orthonormal basis of eigenvectors?
So just to be clear, right? All I'm saying is that the left eigenvector here is going to be orthogonal to the eigenvectors that are not E, right? The right eigenvectors that are not E, which is true even for non-Hermitian matrices. What you're talking about is once you have self-adjointness, you can say the left and the right, the right eigenvectors are going to have that property as well, that the right eigenvector should be orthogonal to all the other eigenvectors in this case. But for any matrix, it should work that the left eigenvector associated with an eigenvalue should be orthogonal to all of the other right eigenvectors. So anyway, the short answer is you don't need this to be a symmetric matrix for this to work.
But what about when you took the transpose of both sides? Shouldn't there be a dagger there then, if it's not Hermitian?
This one right here?
Yeah.
Sorry. So yeah, I see what you're saying. Yeah, I'm not. Sorry. I described that in the wrong way. Really, what we should say here is take the left eigenvector equation here. This is really just the formula for the left eigenvector equation. I could write it like A transpose E dagger or something like that, and then I would write it on the right-hand side. But if I'm writing it like this, then it implies that I'm taking the left eigenvector.
And then should all those places where we have the B of E, should there be an epsilon in front of the B?
Down here?
Yeah.
Yeah, so I'm at order epsilon to the 1, so I've divided through by epsilon. Yeah, so I'm sort of skipping the step where I, do all the algebraic expansion out and I match up terms and everything. So yes, these terms all would have an epsilon in front of them, but since they all have an epsilon in front of them, we're just dropping that epsilon. Because there would be an epsilon in front of this, there would be an epsilon in front of this, there would be an epsilon in front of this, there would be an epsilon in front of this, right?
Why is there an epsilon in front of the x1?
Just because when you expand out x of epsilon, right, the leading order term is
Oh, I see.
E, and then the next order term up is epsilon x1. Okay. So that's simple eigenvalue problems, okay? If you want to read Hinch 1.6, okay, we can do a number of other things. Repeat this procedure for second order corrections, okay? Given repeated roots, we'll have multiple conditions, okay? So you'll have to sort of apply more equations at order epsilon to the 1 in order to specify your eigenvalue, and then you'll have potentially repeated eigenvectors. So you'll have, multiple eigenvectors for the same eigenvalue. And degenerate roots, they can lead to fractional power expansions. So you can handle that a number of ways, essentially just by taking an arbitrary power of epsilon that you expand along. Or, if you have experience, you can sort of guess the right fractional power. Okay. All right. That's linear algebraic eigenvalue problems. Okay. Surely in much of the research that you do, okay, you may come across differential operators. Okay. And in this case, everything sort of passes forward, but we're just going to write things using different letters to imply that we have differential operators now, okay? So let's say we have some mathematical model that's given us a differential equation where we have some differential operator, okay? We have some function of y, okay, that could be nonlinear, okay? And then we have our right-hand side that implies we have an eigenvalue problem here. And additionally, we may have some boundary condition, okay? So like, for instance, at order, 1, you may have kind of a classic Sturm-Liouville problem with Neumann boundary conditions, okay? But that's just a linear approximation of some nonlinear model that you have. So you want to go through and sort of correct for the next order up perturbation to that. Maybe, you have a linearized wave equation, but you want to learn something about a nonlinear wave equation, okay? So what do? So to start out, you can solve your standard linear eigenvalue problem, Ly equals lambda y, okay? And as you know, right, this could be an infinite set, right? And just to make distinctions, right, we'll call them alpha m and um, okay? And so this would be like an eigenvalue, and this would be like an eigenfunction, okay? So based on our discussion of transposes last time, you might imagine that for linear operators now, some of what we do is going to involve the adjoint, okay? So if we have a Sturm-Liouville problem, we might already know that L is self-adjoint, okay? Or we could find the adjoint equation, okay? Or sorry, the adjoint linear operator, such that the inner product of LU with V is equal to U's inner product with L star V for any U and V that are, let's say, L2 integrable on A to B, okay? And for this definition of inner products here, let's assume for simplicity that we have real functions, okay? And this is going to be equal to the integral from A to B of U of X, L, V of X, dx, L star, okay? For real functions here, okay? So, you can do your typical integration by parts in order to find out what this adjoint linear operator is going to be, okay? But let's take an example to be concrete, and I'll take one that's nicely self-adjoint, okay? So for instance, let's say Ly is y prime prime. Then in this case, U prime prime V dx. If we integrate up by parts twice, we get U prime V evaluated between A and B, U V prime evaluated between A and B, okay, plus integral from A to B, U V prime prime dx. This would be our L star V here. And let's assume that y prime of A equals y prime of B equals 0 in this case. So we have homogeneous Neumann boundary conditions associated with our linear operator. If we do that, then we know here that this is going to vanish. And if our adjoint adopts our boundary conditions as well, then those boundary terms should vanish as well, okay? So therefore, L is self-adjoint, okay? So some things will work out nicely in that case. So what do we know? Well, we know from prior results on self-adjoint differential operators, okay, that alpha m, okay, are also eigenpairs of L star, great, and real and positive, and they form a complete orthonormal set, and all of those good things that make proving other things much more straightforward. Okay, let's just focus on one of these eigenpairs though. And now let's take a step towards performing a perturbation problem. So let's take one such solution, okay, and we'll perturb it, okay? And we'll say that y0 is our eigenfunction, and we'll call that, u, y0 is our eigenfunction. We'll call it, u k or something like that, right? Lambda 0 is alpha k, that's going to be our eigenvalue. Okay, and so in this case, y of x epsilon, right, is a function of both a variable and the parameter, is going to be equal to u, okay? Well, let's drop the k's. U of x plus epsilon y1 of x plus epsilon squared y2 of x, and so on. Lambda of epsilon is equal to alpha plus epsilon y1, lambda 1, plus epsilon squared lambda 2, and so on. Okay. What do we do now? Okay, we plug in expansion. Okay, we expand, and then we match powers, right? Order epsilon to the 0, order epsilon to the 1. Okay, so if I take the problem, right? What's the problem that I'm looking at? It's going to be this one, right? So Ly plus epsilon g of y is equal to lambda of y. This turns into Lu plus epsilon Ly1 plus epsilon squared Ly2, so on, plus epsilon g of u plus epsilon squared g prime of u y1 plus so on and so on, okay, is equal to alpha u plus epsilon lambda 1 u plus epsilon alpha y1 plus so on and so on. And finally, b u plus epsilon b y1 plus epsilon squared b y2 is equal to 0, okay? So that's our fully expanded out new sort of perturbed eigenvalue problem. We want to pick off terms of each order, okay? So at epsilon to the 0, easy, we get Lu alpha u, okay? We know that works because alpha and u are eigenvalue and eigenfunction of our unperturbed problem, okay? Well, the action happens at epsilon to the 1. So Ly1 minus alpha y1 minus g of u plus lambda 1 u is our order epsilon to the 1 term, okay? We just have our original linear operator acting on y1, which we don't know what y1 is yet. We know alpha, we still don't know what y1 is, okay? We know what g of u is because we know what u is. We know what u is. We don't know what lambda 1 is. This looks a whole lot like what we already saw in the case of linear algebraic problems. What do you think that we should do in this case? Well, what did we do there?
Take an inner product.
takes some kind of inner product, right? So if we take the inner product, right, because this is a self-adjoint operator with U itself, right, we should remove everything that's orthogonal to U, okay? So if we take an inner product with U, what is it that happens? Well, we get Ly1 U minus alpha Y U is equal to Y1 alpha U minus alpha Y1 U is equal to 0, okay? So our left-hand side then is 0 as before. And so now we know that that inner product with the right-hand side is going to be equal to 0. And we can work out what the eigenvalue is, okay? So I'm almost done here. I'll wrap it up and then we'll be done for the day, okay? So the last little bit then is that 0 is equal to minus G of U, U plus lambda 1 U. Work this out, we get lambda 1 equals G of U divided by U, so just the norm of U squared. So we have our eigenvalue correction. And again, it's sort of the projection of G of U along the U direction, right, in terms of functions. Then if we solve Ly1 minus alpha Y1 equals minus G of U plus, now I've plugged in what I got for my eigenvalue here, okay, U. Essentially, I can solve this for a particular differential operator, right? In the case where this is linear, right? I just have an inhomogeneous linear differential equation that I can solve, okay? And in particular, what's called the Fredholm Alternative ensures a solution to this problem. So if you haven't seen the Fredholm Alternative before, we'll start the class with this next time, but essentially it's two possibilities that you have with inhomogeneous linear problems, right? Either your inhomogeneity is going to be orthogonal to the null space of the transpose of your linear operator, and you'll have a solution, or you don't have a solution. So it's essentially a solvability condition on an inhomogeneous linear problem in this case. Okay, so we'll lead off with that next time. And there's also an allusion to it on the problem on your homework that sort of covers this. All right. Questions about this?
Is that lambda 1 a Fourier coefficient?
An interesting way of.
Because, I mean, looking at that equation on the other side, when we take the inner product, since they were orthogonal terms, it just reminds me of Fourier series, and that kind of looks like it matches. So I was wondering if there's some shortcut.
Yeah, I mean, I think in general in this expansion, right, each of your corrections to each of your eigenvalues, yeah, because each of your eigenvalues is associated with a Fourier mode, you could think of them, yeah, in a similar way. But you know, the eigenvalue itself is not a Fourier coefficient. It's, you know, it's sort of a decay coefficient, for instance. for for maybe the larger problem that this Sturm-Liouville problem is associated with. But yeah, but it's sort of, yeah, it comes about through the same principles that a Fourier coefficient would, because yeah, you're only getting things that are projected along the dimension of this Fourier mode.
And then I also wanted to ask about the Fredholm alternative. I know that it's not necessarily satisfied for infinite dimensional operators. Are we going to talk about when it is satisfied, or are we just going to assert that it will be true for the problems we look at?
Well, yeah, I mean, I'll give you a condition to check. Yeah, and I guess, yeah, I guess when you say satisfied, you mean, you know, the condition that you need in order to have a solution is satisfied. Yeah.
Well, or rather that the Fredholm alternative doesn't apply to all linear operators, but some linear operators do satisfy it, and it applies. Like, I know that like finite dimensional or compact operators do, but
yeah, you're saying infinite dimensional operators don't always satisfy?
correct.
Yeah, I mean, it just depends on the problem that you have, right? So it's not, Fredholm alternative isn't a statement about operators. It's a statement about problems that operators are nested in, right? So because it has to do with the inhomogeneity that you have in a particular problem, right? You know, this is our linear operator here, but then we have this inhomogeneity here, right? And so whether a Fredholm alternative is satisfied or not depends on that inhomogeneity. Well, this whole right-hand side. But essentially, this process orthogonalizes this right-hand side so that your Fredholm alternative is satisfied.
So
So
I know the
Fredholm alternative is not a statement that you can sort of check about a particular operator, right? It depends on a problem that the operator lives in.
So I thought the alternative said something like either there is a unique solution or there exists a solution that's non-unique if a
Right.
certain condition on G
so the question is a
exists.
solution to what? It's a solution to a problem that involves an operator, right? But the operator does not fully specify the problem.
Well, so the alternative is that either there's a unique solution or there exist non-unique solutions if. But I thought that not all operators necessarily had that one of those two things to be the case. I thought it was a condition on the operator that they had like a Fredholm index of 0 or something.
Oh, I see what you mean. Yeah.
So I know that like for compact operators, the alternative holds, it's one or the other. But for other operators, it's not necessarily the case that it satisfies this one of the two alternatives.
Right. Now I see what you're saying. Okay. Yep. Right.
So will we discuss or prove that our operators satisfy the alternative, or is that sort of, we'll just sort of take it for granted?
Yeah, the ones that we will deal with, you can safely assume that that's true. Yes, that the alternative makes sense in that case.
Yeah. Cool. Thanks, Zach.
All right. Okay. Sorry to go a bit long, y'all, but yeah, that's it for today. Remember, I have office hours at 4 today for homework questions or whatever else. And then also tomorrow at 11. So see you then, or see you on Wednesday.
If possible, would you be able to hop on like 5-10 minutes early to office hours? I have a class starting at 4:10, but I'd like to just pick your brain on a few things.
Yeah, I'll try and do that.
Okay,
yeah.
No worries.
So
if not, I can make Tuesdays.
3:55.
Yeah.
Oh, okay. Yeah, I can do that.
Thank you.
Yep. You're welcome. Bye, everybody.